So yeah, my name is Brad Silvers. I'm a Director of Customer Quality for Qorvo. What that means is when our customers have issues, that comes back through my team. So we're in charge of keeping them happy and not just taking them out to dinner and carrying their bags when we're traveling. It's a whole lot of investigating issues with them, explaining to them issues that go wrong, and making sure our parts are high quality so they don't have problems. So a little bit about Qorvo. We do a whole lot of RF, so we're really at the center of it all. That includes everything from, we have parts in satellites, we have parts in base stations, we have parts in just about every phone. Probably everybody here has a Qorvo part in their pocket that you didn't know about. So last year, $3.1 billion, and that's pretty amazing considering it comes in tiny little pieces. Some of those parts in the cell phones may only be a couple cents, but all of it adds up. Play some important roles in the RF infrastructure. So it's a pretty cool company. What I always get bummed about is every time a new phone comes out, it's all about the screen, the camera, and all that cool stuff that everybody sees. But what actually goes every year when a new phone is released is a whole lot of design work. That whole RF architecture is really redone every year. We're getting out more power and reducing current. Brings in a whole lot of challenges because every year we have to re-win our business, basically. And we have very steep product ramps. So what that means is we'll spend maybe 2 years developing a product, and then in that 2 years we will maybe make, I don't know, 10,000 to 100,000 parts depending on the customer and the development work. And then after that 2 years we get ready to ramp into production. So within 1 month we will go from totally building at the most a couple 100,000 parts. We're going to then start building 100,000 per week, and by the end of that month we're typically building maybe 1 million to 4 million parts per week, depending on the customer and the parts. So a very steep ramp. We need to make sure that as soon as we go into production, that we're not going to have any quality issues, because they can become very costly very quick and really impact the customer's ramp. The other thing is very high quality expectations from the customer. Now, I came from automotive industry. I've been with Qorvo now about 10 years. Before that, I was 10 years automotive. And one of the things I thought when I came into consumer electronics is this is going to be so much easier. I don't have single-digit PPM expectations for meaning, less than 10 parts per million fail. What I found out is really hasn't become too much different now in consumer electronics. Everybody expects their phone to work. Right? If you plug it in one day and it doesn't turn on because parts shorted out, right? Consumer's going to be upset and it's going to affect that company. So more and more now, there's really not much difference between the automotive quality expectations and the consumer electronics expectations. So trying to balance that high quality with a very quick product ramp, it involves a lot of challenges. So we do a couple things to make sure the customers stay happy as we're going through all this. One, we do a lot of focus on quality and development. All right, so from the time we initiate the part development, we have quality engineers that are overseeing that process, maybe not overseeing, but involved in the process and thinking of ways that things can break. They're working with our manufacturing teams to make sure any new manufacturing processes we use are manufacturable, that we don't have very low yields, that we can actually ship when we intend to, and we don't have unplanned quality problems. So hopefully that all goes well, and then we'll move into mass production. And when we do, then we have a lot of monitoring we do. And what we really hope is that this isn't needed and it's really boring. We don't find anything. That would be their best case. But we look at both yield and reliability monitoring. Reliability monitoring means we will build up parts and then we'll put them into a stress test, maybe a temp cycle, range from -40 to 125 C, and do that every hour for 1,000 cycles. Make sure the part still works. And we'll do that every week, maybe a couple hundred parts. The other thing we do on every lot is we look at yield, and we make sure that it's acceptable and it's normal. So that's what I wanted to talk about today, is how we do our yield monitoring. It's been the process controls that go along with that. So what we found in automotive is failures are really giving signals every step along the way and every yield point that we have. So here's a pretty simple process flow, right? We got a generic integrated circuit there that's all packaged up. That goes into an engine control unit, right? So we'll send it off. I actually worked in that first box. My customer there was the engine control unit back when I was in automotive. And then that would get tested, and then that lot would ship out for vehicle assembly. The goal was when you turned on the car at the end of the line, you could drive it off the line into the parking lot. Well, if it didn't start up because of a problem with the ECU, you'd have failures. They measured them in ppm or parts per million. And then they would go back to my customer and said, hey, we had these couple failures. Customer would start investigating it. And often what they would find is they would have maybe 100 ppm of failures in their line. Right? It might have been lost in higher yield issues, right, that they normally see. They would send that information to me, usually on like a Friday at about 3 p.m. It's very nice of them. And as we would start looking into what was the cause of the failure there, we'd find similar issues at a higher level in our line. So what this really drove through the industry is to monitor those yields and be very critical of every lot that we send on. Right? Parts are manufactured in lots, so there's a group of them, maybe depending on the part, from 10,000 to 30,000. And we monitor those yields. So it really comes down to 3 steps for this yield monitoring. First, we want to identify lots that are different, right? And then we want to investigate them and understand why. Why are they abnormal? Maybe it's not a big deal. The last thing we want to do is disposition them. We can't just keep holding them and say that they're different. We need to figure out, can we ship them? Do we need to scrap them? Can we rework them? So to identify abnormal lots, anybody familiar with statistics here? Six Sigma, right? So you just, here's a plot of different lots, just generic plot, and our yield. So it looks like we're yielding pretty well. You can always do an average, right? And then a -3 sigma from that average. That's an okay way to do things. The problem with yields is yields are pretty one-sided distributions. If you look, our average here is probably like 88%, but you can never have a 105, 110% yield. That distribution is going to be really skewed high to that one side and then with the tail off lower. So a -3 sigma limit, well, you might catch that part, right, depending on how you calculate that. It's interesting what our statisticians at Qorvo do. They really don't aim for a 3 sigma or using some interquartile. They really backtrack to that method, and they really just look at a yield chart and say, where's the right place for it to be? Right? And the human eye actually, when you're thinking of trying to find outliers, is pretty good at determining where that line should be. So a lot of the calculations that we have into it are actually just trying to mimic where somebody would look at this and say, what looks abnormal? Where should I put that line? So now we've identified something. Now this can be on an overall lot yield. We also do this on individual tests, things like leakage, contact. We want to detect if there's a high number of shorted parts. Things like that are good indicators of a latent quality issue. So then we start investigating it. So there's a lot of things we can do in the investigation. Typically, we start out with data and physical analysis. So we'll start looking over the test data, and then we'll submit parts to FA. We typically find 2 types of things. If you look at these test distributions, right? So I just have a test value here in the count. So the higher here, there's more parts at this test value, and test limits there in red. Sometimes we'll just see a shift in the distribution, right? Just maybe normal process variation. We'll get some more parts that are a little bit lower in output power, have a little bit more leakage. We may look at that and say, that's not a quality concern. That's just variation. We can even do some FA to verify that. The other thing we can see is a bimodal distribution, where the main distribution is still centered within the limits, but now we're starting to see the second group of parts pop up. Typically, whenever I see that, I start getting worried. Just what's driving those? And depending on the parameters, too. If we start seeing parts that have no power output, or they're shorted out, have very high leakage, it starts getting us worried that there's a quality issue. So those are the types of parts that we would submit for failure analysis. Once we have that information, right, we're going to figure out how we're going to disposition these parts. Now, they're different. The yield's different, but that doesn't make them bad. There's a lot of parts that just have lower yield, like I said, because of process variation. We don't just want to chuck everything that's different in the garbage can. So we do a lot of work then to figure out what's causing that and then determine what we can do with it. We can test the tighter limits and maybe weed out some of that stuff right on the edge of the distribution. Or we can just scrap it. Maybe it is bad. Maybe it is a quality concern. Some parts we do just select to send on as is. An often favorite is just, let's just keep them there, continue to investigate, and we'll figure it out eventually. So basically, that's how we do things. I think more interesting now is going into actual case study. So this was a fun one we've worked on before. So we're ramping up a new power amplifier module or pad module for a large customer. These are pretty neat parts. This one, I think, I had about 50 parts in the BOM, and it measured about 5 millimeters by 5 millimeters square. So parts included power amplifier, gas die. We had a silicon CMOS controller. We had switches in there on SOI. We had these bulk acoustic wave BAW filters for RF filtering. And these were all then mixed with surface mount components. They're put on a small board, a PC board, soldered down, and then overmolded to give you that little integrated circuit that's, that we ship out. So talk about that BAW filter. So this part right here is much larger than it is in real life. That BAW filter is typically about 0.7 by 1 millimeter. These can get pretty small. You can get them mixed up with pepper if you drop them on a table. The way we connect those to the board are with these copper pillars. So these black circles here are actually plated up copper, then with plated tin on top. So we would make a wafer. So there's a round disc that may have 10,000 of these on one of these wafers, and we plate up all these bumps. And then when we go to assembly, we'll flip them onto the board, reflow them, and overmold them. Well, so we started up this ramp, big customer. This is a very important part, very complicated, and we start monitoring. Right? We start looking at the yields. So this chart was the actual yield, and each color is a different work week. So you can see that ramp that I was talking about, where there's not a lot of lots in the first couple weeks, and then it looks like about 5 weeks in, we hit some big volumes. And things went well at first. But about 3 weeks into high volume, we started getting a whole lot of fallout here, where our limit was 99.8%. So this is a leakage test, which we expect to be very high. And we started getting up to 10% fallout for these. So it was a huge concern. I think we actually shut the line down for a little bit as we were investigating. And we pulled out parts and performed FA on them. All right, what we found is, we talked about that copper that's plated up there for the interconnects. Well, there was extra copper that was shorting between those two bumps. So here's a reference, and then the deprocessed part. So what we're looking at is the bump, another copper bump or copper pillar. There's test pads here, right? And then on the deprocessed part, now, one, it looks ugly because it's been in a overmolded package and you have to use mechanical polishing and then acid to decap it all and expose it. But you clearly see all this copper here, right? That should not be there. So once we started running the part, you have the ability for the copper to migrate and actually short out those two pillars. And that's where we're seeing the leakage. It's kind of interesting. This was a RF port, so we're actually putting DC through the antenna pin. It was actually testing another part elsewhere in the module, and testing out some capacitors there and making sure that they were there. But we were able to see leakage here. So it's kind of neat. We were testing one part, and we were able to see a signal somewhere else. So now we know the root cause, right? So it looks like our yield monitoring has worked, right? We had abnormal lots. We caught them. We were able to stop and look at them and figure out what happened. The fab engineers were able to go back and figure out why we had this problem and fix it. But what we started looking at is, well, why did we even build them into modules, right? Similar to how we had that 3-process flow earlier with the integrated circuit fabrication and then the ECU fabrication. Well, these parts are made in our fab, and they go through electrical test and an optical inspection, and then they're shipped to our assembly site where we put them into that multi-chip module. We started wondering, well, why did we even build with those to begin with? We started looking back at the yield signals back in our fab. Electrical looked okay, but as we looked at the automated optical inspection, we found it wasn't so good. So this is a pretty cool machine, right? We have a wafer with these 10,000 parts on it, and it has a camera, and it will scan through, take a picture of every single part, and compare that to a known good part. And it will actually compare pixel by pixel if anything's different, and that's how it defines a defect. Well, what we saw wasn't so great. Here we had most of the lots are down near 0%, maybe a 5% yield loss, actually. Sorry, this chart is backwards. But But we had a number of lots, especially a couple weeks in, where you had these wafers with, look, up to 20% loss at a visual inspection. And although we knew to look at the module level, we weren't looking back at the fab level for the AOI inspection and seeing, was there anything abnormal there? But one of the things we started talking about is, well, if we're inspecting them out, why are we ever seeing a problem? Right? It's taking out all the bad die. All that's left is good die. So here's a wafer map. So there's 10,000 dots on there. You can count and verify if you'd like. The blue die are the bad die. Those are the ones that the automated optical inspection machine said was abnormal and screened out. We started looking at some of these wafers because in the middle of that blue splotch, maybe is the technical term, you have a bunch of good die, right? So we went and started looking at those, and lo and behold, they weren't actually good. They were getting through our containment. So this was one of the die from that area, and you can see copper in between the two pillars. So we had a containment that wasn't 100%. So we went back learning from this and did a couple different things, right? We created an improved automated optical inspection program. So in green now, we can capture more of those die that have the problem, pretty close to all of them. So enough that we could get an even higher yield signal if we had a lot through that had this issue. We also just implemented yield monitoring. Did the same thing we're doing at the final module level we did at the wafer level. And we're able to capture lots coming through that have this issue, and we don't send them on and don't build with them. And the difference when we capture something back at the wafer level, we're talking about parts that are a couple cents to parts that are in the dollar range once we put them into the module. So it's very important to catch them early. So now is the tough time. We built all this stuff. We want to know if it's good or bad. So we started with our disposition plan. We said, well, we'll do reliability testing. We have all these cool tests that really stress the part and figure out, hey, are these things going to fail for the customer? So there's a number of different tests we did in pretty high quantities. So typically to qualify a part, you're doing 77 pieces in each one of these tests. Here we took 2 different lots, and you can see we ran 40 to 240 parts through each test. HAST is a neat test, so we're actually putting it at high temperature and then pressurizing it to force moisture into the part. You had a question? 5 minutes. Oh, 5 minutes? Okay, I should be all right. Should be all right. So we went through all these tests and had no failures, right? So success, we could ship those parts. Then it was pointed out, where did those parts come from? If you remember that wafer map, well, there was a whole lot of good area on that wafer map that wasn't affected. So did the parts that we tested come from here? Or did they come from outside of that area? Well, we really didn't know. So that forced us to actually go back, be a little bit smarter about how we pick parts. We came up with a new disposition plan. So we wanted to pick die that were next to those bad areas because we knew that those were the ones that were getting through and getting built into our modules. So we actually came up with 3 different groups here. So the red was the AOI. I switched it around on you from the last one. Blue was good now, or bad before. Now red is bad. The light blue are ones we decided to build into modules to determine, hey, are those parts that we shipped out in that area good or bad? And then as a backup plan, we took these dark blue parts and said, well, worst case, we can exclude all that light blue area and just ship out the rest of the wafer. We could use those parts to build, kind of limit the impact. So we built up these parts, ran it through, and depending how you look at things, it was either good results or bad results. It was good because we got a signal there. From the light blue area, that middle area in between all the bad die, we did have a failure. We were able to do FA on that and find that, yeah, it had the same issue. All right, so unfortunately, the parts that were already built up, we couldn't save. They had bad material in them. There was no way to screen those out, and it's going to be a reliability issue for the customer, and we had to protect them. But we did find that we could save portions of those wafers that we had built up that were affected and use still a majority of those die, so maybe not a total loss. So we learned a couple things, right, that all these yield points are meaningful. We've been implementing more and more of these now in our process. And anywhere we're taking a yield anywhere we're doing measurements, we want to look at that and say, are those parts abnormal? And let's catch those before they get to the next customer, whether it be an internal or an external customer. We also really question our effectiveness of our containments. When it comes to reliability issues, tests are often good at catching, parametric problems, parts that are bad right now, but it's very hard for an electrical test to catch a part that's going to fail in the future. We're talking about a test that may be in the, 500 millisecond range that is going to be used in a part that's going to, in a phone, run for minutes. In their test, and then hours and hopefully longer out in the field. So we really need to make sure when it comes to latent issues, we rely on the yield data to identify bad groups of parts, because identifying bad individual parts can be very tricky. All right, so I think I'm about out. So now one of the things I do as customer quality is I often talk about things other people do. So there's a couple great engineers that actually did a lot of this work that I got to talk about today. So I'd like to thank them. If you ever see Harold or Zhao Kong, they're in Texas, so maybe they won't be here today. But thank them. All right, any questions? All right, thank you.
I actually have a question for you.
Sure.
You had an orders of magnitude kind of chart showing how the number of parts per million changes. I would expect it to be the opposite. Like if you were going from the IC and you have a certain ppm yield loss, then you integrate into something else which has a whole bunch of other parts. Wouldn't that integrated thing have a higher yield loss?
It could, depending on the defect mechanism.
Okay.
Most defects, right, you have a higher level right as you first test them, right? You have some that are just bad right off the bat, as we saw in our actual electrical yield loss. But that weeds out a whole lot of the parts. So in this case, think of it, the example that I had, there was metal that was very close to being shorted out, but not quite shorted. So some of those were different lengths and distances away. The ones that were shorted right away would fail very quickly.
Oh, so this is after you've weeded out the bad ones.
Right.
Okay.
Yeah.
I get it. That makes sense. Great.
Well, I guess this is weeding out the bad ones.
So the step between the 1,000 ppm to the 100 ppm, you've tested a bunch, you've thrown a bunch out, and you only send the good ones on.
Right.
And that's why it's a lower number. Okay.
Well, yeah, we try to send the good ones on.
Got it. Yeah. Okay.
So Thanks. I had a similar question, which I think you've now answered. But just to be clear, so the way I decided that I should interpret this slide was that's kind of what you were aiming at on the way out. That's right. Your chips. If you had 1,000 ppm yield loss at the chip level, that would be okay. But if you had 1,000 ppm yield loss at the ECU level, that would be really bad for your business, for your ECU business.
Exactly.
And so about 100 ppm is about what the ECU business can cope with when they ship their parts out, right? And when you're shipping the cars, is that a right way of thinking about it? You want even lower.
Right. You want 0 at the cars. So the target everywhere actually after our module is 0. Right. It should be 0 for catching everything right off the bat.
So is this yield loss strictly due to that IC, or is it the yield loss for the entire integrated product? So tires, headlamps, like
right. So this is looking at for this issue on the IC.
I see. Okay, that's why I was confused then. Okay, great. Cool. Let's thank Brad one more time. Thank you.
Thank you.